Okay, so this is the second video in chapter 11. Please note that this is going to have some different types of things. I think we're going to be watching some other videos from YouTube and so forth during the duration. And I've posted those videos as well in the additional videos portion of the Moodle link. So just have a look at all the different resources on Moodle and kind of follow my advice as you go along, okay? So you might have to be patient in this one. Anyway, so we're going to look at a lot of different stuff. So first, as you note on 292, they compare harmonic motion and circular motion. So I thought we might first just look at a little applet. So I'm going to bring that applet up, and then we'll go back to what we have in the video. Okay, so let's look at that applet. So here's the applet. So notice we've got two different springs. We've got a vertical spring and a horizontal spring. So let's start the applet and see what happens. So first, this is just to show you that for something that's moving around with circular motion, that is also simply harmonic motion. So you can see that as it's going in a circle and it's keeping track, for instance, of this vertical spring that's attached at the same point as it throughout that circle, look at what kind of path we've got here. Can you see how this is a sine wave? It looks like it's a sine wave because it starts at the origin. So it could be a sine wave or cosine wave depending on where you start. Okay, so let's reset and let's see, we can drag it different ways. So notice if I kind of remove that and we just look at it straight on, let's look at how as you look at it straight on, you can see that this is basically simply harmonic motion. So let's start it. So as it goes back and forth when we look at it, that is simple harmonic motion. So I think a big point that the book makes is that the period of simple harmonic motion is found to depend on the stiffness of the spring and also on the mass that's oscillating, but the period doesn't depend on amplitude. And I think that's found from thinking about this as you look at it straight on. So as you look at it straight on, you can't tell, but if we pull it out, you can see that, try to grab it. Well, now it doesn't want to let me grab it, but if you pull it out, you can see that it's actually a circle. So even though we can't tell, simple harmonic motion has something to do with like the period and amplitude of a circle. So I think that this is a really good way. So I'm going to leave this applet on there, and I would mess around with it and maybe try to analyze it a little bit yourself. So it's pretty interesting that you can view simple harmonic motion in terms of circular motion. That's pretty interesting. Okay, so let's get rid of that guy. So you can play with that guy some more on your own, if you like. So here is the book. Get a nice screenshot of it. Okay, so here is the book's picture. So if you're looking straight on and you see an object that's really attached to a circle and you look at it straight on, the position of that object, x, can be considered to be the simple harmonic motion of like the spring that we're looking at in the last video. So that's a pretty interesting little piece of argumentation, I guess. So I'm going to ditch that guy now. We're just going to look at the circle part of it. So let me go grab this circle. So we might pull up that circle in just a second. Okay? All right, so the first thing is let's look at the circle part of that motion. So let me grab that and kind of position it right here. Okay, so let's just confirm that it's the same kind of simple harmonic motion that we had for a spring before. So first of all, the object is traveling around, just like we saw in that applet. So as it travels around, its velocity is going to be constant, and that constant velocity is what we're going to call its maximum velocity because it's not going to be greater than that. Its tangential velocity, or excuse me, its velocity with respect to the x-axis, we've got our coordinate system right here, x and y. So its velocity with respect to the x-axis is always going to be changing as we go. So at some points it's going to be exactly the same as the max velocity. That's when it's like up here. That would be when the spring is at equilibrium, right? Because we said its max velocity happens when it's at equilibrium. So if we went back to that applet, we could see that right here at the top of this circle, the velocity and the max velocity would be the same. That's when the spring is at equilibrium and it doesn't have any potential energy. It's all kinetic energy. It's going to have the most potential energy at these two spots on the circle. So if you want to play with that applet more as we have this video, as you have this video going, that might be a nice thing to do too. Anyway, so the book's first argument is that we have similar triangles between this triangle and the triangle keeping track of the position. So we have a triangle keeping track of velocity with respect to theta, and from geometry you have like alternate interior angles and some other stuff that show that these are the two same angles. But anyway, so this one controls velocity, this one controls position, and also the amplitude. The same thing we had last time, the amplitude of the spring. So you can notice that A isn't really changing. So like for right here, if we thought of it before, then that would be the amplitude of the spring. Okay? So there we go. So they say from similar triangles, you can conclude that the ratio of V to V max is the same as the ratio of this side of the triangle. That's come from the Pythagorean theorem, right? This side of the triangle to the amplitude. So let's think about that. If we look at theta, we've got that side of the triangle. If we look at theta, we've got that side of the triangle. So isn't V being compared to this thing? V and that thing, there you go. And if we look at theta, the hypotenuse of the triangle is V max, and if we look at this guy, the hypotenuse of the triangle is A, so you've got V max compared to A. So they're just saying, since those are similar triangles, you can write that little ratio. Okay? So don't think it's so hard, it's just a little proportion because of the similar triangles. Anyway, so let's go through solving for V in this situation. So they're saying solving for V, you can go these two steps. This is a really nice thing. We do this little trick in calculus, stuff like this a lot, so I thought it'd be good to look at this algebra trick. So notice, I think the way that they did that is they said, hey, if we want this A to go inside that square root, how can we do that? Well, we can square it. If we want it to move inside a square root, we can square something. If we want something to come outside of a square root, we of course square root it. But you can also take stuff like this A and put it inside that square root by squaring it. So because the square root, of course, of A squared is A. So if we don't want to go this way, we can also go this way. That's something you probably haven't done very many times yet, but you're going to in calculus, so it's pretty important. So we want to go A to A squared, so we say, hey, how can we do that? We can say, let's just stick this guy in. So we've got A squared minus X squared. That's already underneath the square root. But if we square A, now it can also go underneath the square root. And now we've got this thing, which if we split it up, A squared over A squared is 1, and X squared over A squared is X squared over A squared, and there we go. And then they also took the V max and multiplied it up to the other side, so you can see that. Okay? So there's where that came from. And now what's so important about that is that, remember, this equation right here, this guy, is what we had derived another way for that spring that was oscillating back and forth. So in other words, for our circle, if we view it in this way, so that X is measured from here to here, and we think about the spring bouncing back and forth from here to here, this situation is exactly the same as that spring that we had oscillating with simple harmonic motion from before. So we've basically done a little pseudo-proof. It's not a complete proof, but it's a little argument that shows that that spring moving back and forth from before is the same thing as this point moving around on a circle and us kind of looking at it from the side view. So such a neat argument. I think it's beautiful, but you know, it is a little bit complex. Anyway, so then what we're going to do from that is we're going to think about frequency and period. So it says we can now determine the period of the simple harmonic motion by thinking about the circle instead of thinking about the just spring motion from before. So we're going to use this circle to come up with the period of that simple harmonic motion for the spring and for anything else that works like that, that's moving back and forward like that kind of motion. So really nice. So all we do is we go distance equals rate times time, and we think about going around in a circle, and we say, okay, what's the distance? Oh yeah, you know what? The distance was 2 pi r because that's the circumference of the circle. We said that the rate, basically the speed, was the same. If you remember, we didn't change it. If you look at that applet, it's not changing over time, so the rate is just always v max for the point that's moving around the edge. That's how fast it's going. And the time is going to be, if we go 1 revolution, we'll say that that's equal to the period. Okay? So you can clearly see that if you solve that, you get v max equals 2 pi r, and from the way we had this set up, isn't the radius equal to the amplitude of the motion? That's the way it works if we're equating it to the spring from before. So 2 pi a over t equals v max. That's how they got that. Remember, 1 over t from before, if you have 1 over t, let's just write it down here. 1 over the period is the frequency of the motion, how often that occurs. So I'm going to show you another video where that's going to be broken down a little bit more, and you'll have access to it on Moodle if you want to review that as well. So someone else breaking that down. Okay, so the reciprocal of period is frequency. We did mention that before, though. Anyway, so then they say, okay, solving for the period, so then they're going ahead and solving for the periods. Let me grab my blue again. So they say, well, then that means that t equals, from this equation, you multiply it up there, and you get 2 pi a. You divide your v max to the other side, and that means that's an expression for the period. But we can simplify that further because a lot of the time we won't know necessarily our max velocity directly, but we will know like the spring constant and stuff. So if you remember from before, in the last video, we said that from the conservation of energy, at equilibrium, all the energy is kinetic. At the end of the motion, for instance, at like one of these points over here in this diagram, all of the energy is potential. So we said those are two different expressions for the total energy. And notice that involves V max and A, what we have right here in our expression for the period. So if we solve that, we can say, can we get A over V max somehow? Let's see if we can get it to look like that. So we can get rid of those 1/2, right? So then we can say A squared, let's see, equals m over k. We divide the k to the other side. V squared max. That's really close, isn't it? So we want a over v max. So maybe I'll square root both sides at this point. That might be a good idea. So I'll square root both sides. That'll get rid of these guys, right? So then we'll have a equals the square root of m over k v max. So if we want a over v max, we just divide and we have it. So a over v max is the square root of m over k. Right? So in other words, for simple harmonic motion, an expression for the period, or for circular motion when you view it from the side with this kind of coordinate system, is that you have 2 pi square root of m over k. And that's the period for any type of simple harmonic motion now. So that is a pretty darn powerful argument. Of course, from this same reciprocal identity, if you want the frequency, you just invert that. So you say, hey, flip everything. So you have 1 over 2 pi, and then you flip the stuff inside the square root, and that's the frequency. So you have the frequency and the period for any type of motion which has this backwards, forwards type of situation, which is all kinds of stuff. We're going to talk about sound waves, ocean waves, anything that moves with waves, basically, is going to be simple harmonic motion. So why is it anything that moves with waves? Well, you can look at the conic videos, and you can also just look at the rest of this video. Okay, so we're going to start to break that down, that wave aspect to the motion. Okay, so hang in there with me. The next thing I would do is pause this video and go watch the Kahn video on angular velocity. It, from a very basic level, breaks down what angular velocity is. Angular velocity is the notation, the variable for that is this omega thing from the book. So I would go watch that now and then come back to this because I'm not going to explain it. I found that video, so it was a good explanation. I thought it was basically exactly what I was going to do. So you might as well pause this now and go watch that. Okay, so whenever you get back, now we're going to think about this and see exactly how it works with a wave. All right. So notice first it says if we go back to that circle that was undergoing simple harmonic motion, we can see that cosine of theta equals x over a. So let's bring that circle back and look at it again. Okay, so here's that circle that we had from before. We're viewing from the side. And if you look at the little basic triangle that describes the position of the particle with regard to theta, you can see that the cosine of theta is going to be x divided by the hypotenuse a. So if you rearrange that, you have an expression for the x position of the particle as it bounces back and forth. So when it's right there, its x position is this much. If the particle were over here, we could draw a little triangle like so, call that theta, and its x position would now be this much. But it's always going to be controlled by the amplitude of the motion times the cosine of theta. Remember, the amplitude is just how far the particle is at its greatest displacement. So now here's where we're going to use what they got from last time. So because the mass is rotating with this angular velocity omega, which you're going to have watched the Kahn video on, so omega is kind of the angular velocity right there as it goes around the circle. We can express theta in terms of omega t, okay, where theta is in radians. So in other words, we can just basically replace theta with omega t. Okay? So the next step is that another way to replace theta basically is to say that omega is now 2 pi times the frequency. So let's bring up another video, and I'll also post this on Moodle, but let's just kind of watch it together. It's this really super loud guy, but I think he does a good job of explaining it, at least as good as I could do, but just, you know, to do something different as well. Let's bring that up. So the end point here is that the position of the particle in simple harmonic motion can be described by a cosine of theta. We replace theta with this omega t, the angular velocity times time. And then we can replace omega with 2 pi times the frequency. So at the end of the day, our position of the particle can be described by this cosine wave expression, where we have 2 pi times the time of the particle based on how long it's been moving over the period it takes to complete one full cycle. And that's really the big key for simple harmonic motion. And also, the Kahn videos kind of attack this from another angle, so it'd be good to watch those. But the thing we haven't done yet is we haven't talked about why omega is 2 pi times the frequency. So let's bring something up and watch that. Alright, so let's see, I found a nice video, this guy's video, and I'll also post this online. So let's make this small so we can see it. And he's really loud, so prepare yourself. Here we go.
So let's suppose we take the following object, a disk. Now, because the width of the disk is much smaller than the length or the height, we can make the assumption that we're dealing with a two-dimensional object, like the object shown on the whiteboard. So let's suppose we take our disk and we rotate the disk in a counterclockwise in the positive direction. Now, because the disk is rotating, it is undergoing a...
So you can see that this situation that he's presenting is perfectly analogous to our simple harmonic circular motion that's also coincidentally moving in a counterclockwise rotation. So it's perfect for us.
Rotation, the object, that this is said to have angular velocity. Now, recall angular velocity is simply the number of radians that our object rotates per some given unit of time. So the units of angular velocity are radians per second. Now, recall that frequency is simply the number of revolutions, number of full rotations our object makes per some given unit of time. And that means the units of frequency are revolutions per second, which is known as hertz. So 1 hertz is equal to 1 revolution per second. Now, let's suppose that our circular object rotates 1 full rotation, makes 1 full revolution every single second. Now, because 1 revolution per second is equal to 2 pi radians per second, we develop the following equation. So we can represent frequency in terms of pi and our angular velocity. So it turns out that frequency is equal to our angular velocity given by our Greek symbol omega, divide that by 2 pi. So this gives us the frequency, and if we want to represent our angular velocity in terms of frequency and 2 pi, we simply take this and bring it over to the left side. And we get the following very useful equation. So this equation relates the angular velocity of the object and the frequency. So if we know the frequency, we can calculate the angular velocity, as we'll see in just a moment. Now, recall that the period of rotation of an object is simply the time required to make 1 full revolution, and it's given by a capital letter T. Now, the relationship between frequency and period is given by the following equation. The frequency is equal to 1 divided by the period. So if we want to, we can also represent our angular velocity in terms of pi and our period. So we simply replace frequency with 1 over period, and we see that angular velocity is equal to 2 pi divided by the period. So these two equations can come in very handy when we want to calculate the angular velocity knowing the frequency. So let's look at one application. Let's look at an example.
Okay, so I think that he did a fair job of explaining why omega is 2 pi f. Another way to think about it is you can use the rhetoric in the Kahn video as well. But, I mean, this really just goes back to distance equals rate times time again. So don't make it too much harder than that. So let's think about this. If we go like that then and we solve for rate, then we get rate equals distance over time, right? So if rate is distance over time, then we can say that the rate here we're going to be considering in an angular sense. It's omega. The distance undergone is the circumference of the circle, so like 2 pi. Well, we're thinking about in terms of an angle now, so we don't need the 2 pi r. Remember, omega, well, I'm not going to go in that direction, but you know what omega is from the Kahn video as well. So we're just thinking about the distance as like 2 pi. The time is like the same. To undergo 1 full revolution is t. So there's essentially what we have right there as well. So don't worry about it too much. This is a really powerful equation, though. That's something that we really didn't cover too much this year. So omega, the angular velocity, is also 2 pi times the frequency. Breaking that down in terms of radians per second and so forth is the way that you get that. So don't worry about it too much. But anyway, so there is a way that we can keep track of the x position of this particle as it moves about this circle, which turns out to be also the x position of a particle that's undergoing any type of simple harmonic motion. So that's pretty powerful. So now all we need to do is, can we figure out the velocity of the particle, an expression for that in terms of when it's undergoing this type of motion or simple harmonic motion, and also the acceleration. So that's what we're going to look at last. So I think it's on page, let's see, on page 295. They talk about velocity and acceleration as functions of time, and they show you this little diagram off to the side. And they kind of go through some different arguments, but they're not really complete arguments because they're missing the calculus aspect. So we've got displacement x, we've got velocity v, and we've got acceleration a. Well, what you should know from calculus, and if you haven't had it yet, oh well, but is that these are all related to each other. Position, velocity, and acceleration are quantities that are related with what's called a derivative. So if you take the derivative of this curve, which we just figured out, right? We just went through a derivation that said that the x position of the particle undergoing this type of motion is x cosine, and then we had 2 pi t over the period. Remember, the variable here is the time. The period is fixed based on the simple harmonic oscillator. The easiest way to think about this is just with calculus and to say, hey, if I take a derivative, I'll get the velocity. So let's take a derivative of that. The derivative of cosine is negative sine, right? So we go negative a sine of 2 pi t over t, and the chain rule says to multiply by the derivative of the inside, so we have times 2 pi over t, because that was a constant. So we pull this part out in front here, and negative a 2 pi over t, if you remember from, I think, the first video, you can say that negative a 2 pi over t is the same thing as negative v max. Right? So you might just go back and check that in your book or in the first video. So you have negative v max, the sign of that same thing. Anyway, so now that is the velocity of anything undergoing simple harmonic motion. You can also just look at the graphs. So notice, let's just check on the graph that these look like derivatives. So the slope of the tangent line at these points is 0, so those should correspond to zeros. Yep, yep, yep. Oh, here. Yep. So, and the slope between here is positive, so this is all positive. Slope from here, the tangent line is negative, so this is all negative. So that looks very much like a derivative. Yay! And then if you want the acceleration, you just take another derivative. So you say the acceleration is going to be, so we take the derivative of this, derivative of sine is, this is a constant. So we have negative v max. Let's write it out like we had before, in fact, this time. Just to see what it is. So what was v max? It was really negative 2 pi a over the period. And then the derivative of sine is cosine, positive cosine. So we have cosine of stuff times the chain rule once again, 2 pi over t. And we see what that is. And let's see, so that's going to be equal to, so we've got the cosine term right here. And this one I'm not seeing directly, but let's see. So we've got negative 4 pi squared a over t squared. And for some reason, they're saying that that is equal to negative ka over m. So let's see if we can figure that out. It probably doesn't really matter, but looks like they maybe substituted t in there. So let's see if we go negative 4 pi squared a over, what's the expression for t? It's 2 pi, we had that in the last slide, right? 2 pi root m over k. So we square all that. Let's see. We square all that, and what do we get? So now we've got 2, oh no, 2 squared, my bad. So we've got 2 squared is 4, pi squared is pi squared. The square root of that is going to be, let's flip it. So square root of square root is m over k, but we're going to flip it and go k over m. Then on top we had negative 4 pi squared a. Hey, I think some of that cancels. Nice. So that's gone, and what's left? Let's see, we've got negative, we've got a k, we've got an a, and it's over m. Look at that, there it is. So there's a little bit of calculus background on this guy, and if you look at the slopes here, notice there's 0. So these are indeed derivatives. If you haven't had calculus yet, I mean, don't worry about this too much. The main thing you need to take away is that for simple harmonic motion, guess what? We have an expression for the position of a particle undergoing that motion at any time t. We also have an expression for the velocity of that motion at any time t. And we also have an expression for the acceleration of that motion at any time t. And using calculus, you can see that it doesn't take very long to get those. I'm sure everyone who's had calculus followed that perfectly. So if you haven't, oh well. Just know that you can use these 3 equations to describe the position, velocity, and acceleration, and just use them, okay? But if you haven't had calculus, this should have been a little bit interesting anyway, I think. So hope you have a great break, and make sure, if you have a chance, that you also watch the other videos that I posted fully, and they'll help you out a little bit more too as well. So the stronger we can be when we get back, the better. Have a good break.